reminder, the two wires that go to the R and the L terminal on your magneto switch, your ignition switch, whatever you want to call that, make sure those are shielded wires. I hate to have it. Well, I guess if you didn't make them shielded, it'd be real easy to go remake them shielded. It's not that much more work. But make sure you get them that way. Okay. Yesterday, I'm going to use the word I was frustrated with myself because a lot of you guys were not using the manuals for your batteries in and out. I told the other instructors, I'm like, it's like they're trying to change batteries on lawnmowers, not aircraft. So I got thinking about it, and I'm like, well, that would be mostly my fault. I'm the instructor, so I should have emphasized more to use the manual when you're doing this kind of work. And if you're using the manual stuff, will hopefully start jumping out at you when you read it. I've got a couple slides that I added to the last 2 days' PowerPoints as we went through, just to kind of point out. So I'm going to go through those a minute, and then we will take a short break and jump into today's lecture. But I corrected that. That's weird. Maybe it didn't save. VRLA, valve-regulated lead acid. You might think, like when we're explaining it, oh, there's one relief valve. But often it's not one relief valve, and they're not that fancy. So this is a photo of the 210 and the Concord battery, and a lot of the Concord batteries that we have laying around here are valve-regulated lead acid. So there is still fluid inside them. In my next slide, I zoomed in on it quite a bit. And they've got a nice label on there that says voids warranty if you cut this, so they basically don't want us in there as mechanics. You don't want to void the warranty. But ABED was like, hey, where is this thing vented? Because even though it's valve regulated, it still is going to go just a little bit every once in a while. And we go, well, that has to go somewhere, right? So the cap itself is not totally sealed down, so it can kind of get out of here. We're not expecting a lot of, so depending on the aircraft and how they're installed, it would be interesting, or even the STC for this going in, how that works. But these little black pieces are basically, let's say, factory engineered. They're set, I hesitate to say spring because it's the rubber, it's kind of how the rubber presses on it. But that is the valve itself. So number one, you're not supposed to get in there anyway. Number two, if you read through the manual on Concords, they don't want you messing with those. But we're in a training setting. So if you have safety glasses on, so it's acid, if you were to just pop the corner of that up with a screwdriver or something, it'll go at you because the battery has a little bit of pressure in there often. So I wanted to give you that picture. That's what most valve-regulated lead acid batteries are going to look like. You could take those out to check your fluid levels and stuff like that, but if you get down into the manual, now this is for a 450. I don't know if this one's specifically 450. I read a couple of the manuals yesterday, and they almost all read pretty close to the same as this. Has no field replaceable components and is not designed for disassembly, reassembly. So basically they're saying, yeah, you're not going inside here. They do give a cleaning section. They say how to clean this thing, and for testing, it ends up getting tested very similar to more of a NiCad, where you're going to pull the battery out, you're going to put it on a bench and do the drain test, make sure it's 80% capacity of what it's rated at, right? That one, I can't quite read what it's rated at. And you're going to make sure that it makes that 80%. If it doesn't quite make it, they give you a couple suggestions for like drain, recharge. But basically what they're saying is you're going to pull it out, test it on the bench, and if it doesn't test, well, if it's under warranty, you get a new one. If it's it's not under warranty, it's a bad battery, go buy a new battery. So there's not any maintenance that they allow you to do. So if it was out of warranty or you don't care about it, there's a little bit of gray area on, well, if it doesn't test at 80, could I check how much fluid's in? Could I add if there wasn't? And you go, the problem is, what are you gonna base your work on? You're not gonna be able to find Concord service manual telling you, added fluid to the level in accordance with Concord service manual, because they're saying you're not going in there from everything I see. So be aware of that, valve regulated, they do have fluids, you could physically check it, but you're not gonna find paperwork to tell you how to do it, which means basically you can't for the most part. We'll end up with that in instrument class with very similar stuff. Fuel pumps are similar. You're always supposed to use the manual for servicing that kind of thing, and the companies will purposely either not provide a manual or they'll not put stuff in the manual for how to do it, just to say, hey, you're not supposed to work on it, so we're not going to tell you. And that's one of the ways they keep you out of a valve-regulated lead acid. So I'm going to use the word makes sense, but you guys tracking with me? Because I don't know if it makes sense. I'm like, really? It makes sense to give you some information, but everybody tracking with me? All right, cool. That was back to the gel one. So I got to flip over one more PowerPoint. Slide maybe? On the wrong slide. Let me back up. That was yesterday's. I added a couple. Where did I add them? Get close. Leo, he's going to be in there for all time. All right. I ran out to the 175 where I put a battery in an aircraft to grab the gill paperwork. Now I did on your PowerPoint also throw in there, you'd have to copy and paste if you want to go there. Question?
For the previous picture, we
That
wouldn't
one?
be able to use the one
We'll go there
with the battery,
next.
but we wouldn't be able to use AC 4313 to repair that at all.
Oh, the valve regulated?
Yeah.
I don't, the problem is, when you say repair it, we're not gonna pull cells out.
Right.
So most of the time, even on a standard lead acid, repairing is going to be, we're gonna use the word serviced. So if you service hydraulic tank, you fill it to the appropriate level. So servicing a battery is you're gonna refill with distilled water to the appropriate level. I believe the issue you're gonna run into is you're not gonna find any documentation on what's the appropriate level. I'm not sure Concord's gonna say what it is. So for instance, if you go to this website for Gill standard battery, it'll be very clear on what level to put the solution at when it's charged, and double checking, and they'll be very clear what level they want. Not gonna find that on the valve regulated. So if you said serviced it, they'd be like, well, how much did you put in? What level did you fill it to? What did you base that on? And AC 4313, I don't think AC 4313, it might talk about split rings. I'm not sure these have split rings. I'm going from my memory on how much. So back to, if you had the battery and you could find documentation, possibly, but they're purposely kind of saying, hey, stay out. Dean doesn't like those batteries for that reason. He's like, they don't let us do anything to them. And he had a couple that went bad, so, yeah. So, it's a copy and paste. If you want to, it'll get you to Gill's component maintenance manual. I ran out there because I was like, I know they gave me the torques on these, and a lot of you guys were like, we can't find the torque on the Gill. So I'm like, I'm gonna run out to the hangar and find the paperwork that came with the battery. So that's what I did, and then double checked online. So on the Gills, you typically either have a bolt, which that one, if we can find the torque level, is easy, right? It's just a bolt. Or you have this, calls it a wing nut, and one of you sharp students, I gotta give you credit. One of you sharp students actually went to AC-43, I can't remember who it was, David, and found torque for wing nuts, and AC-43 had said wing nuts are basically by hand. And he's like, so I have a wing nut in the picture, AC-43 says by hand, so we're going with by hand. And I was like, okay, that can't be though. Until I can prove you wrong, we'll go with that. So that's why I ran out there. Does still say wing nut, but we're gonna find in Gills where they do give us a 50 inch pound. I've got a couple different places where it says that. So this one's just showing the two, and here's one spot in the maintenance manual. This was a sheet of paper, you can see my ugly thumb, that came with the specific battery I have, and it's back to 50 inch pounds, 50 inch pounds, 50 inch pounds. Was it the last slide? Yeah, right here. The wing nut fits a 5/8 or 16 millimeter 12-point socket. So basically, what you can do on these is a socket, they say 5/8, doesn't drop down perfectly, maybe the 16 millimeter is a little bit better, but it pretty much drops on there real nice, and you can turn it with that. So you can torque those wing nuts appropriately to the manufacturer's specifications in that manner. Some of you guys were asking me, how do I torque those? And I'm like, I know it's like a socket, I can't remember, a crow's foot. So I went back and got the info. 5/8 socket goes right on the top, and they torque it down nicely. I'll even pass that around the room. All right, is that making sense and clear to everybody? Batteries especially, we want to be really careful that we do have those torqued correctly. We're very high amp draw. We don't want those coming loose, ruin our batteries, starting fires in the aircraft. I would, man, as a mechanic, if you can't find the torque or you can't get it right, don't release the plane. Don't send that back out. But yeah, all right. That one. This was, I just pulled it off the same manual online for the fun of it. I think I showed you this in general class, but for that particular Gill battery, they have you put the battery in initially at 800-ish hours, or just under a year. It's 11 plus or minus 1, so basically they say not more than 12 months after you install the batteries, how you read that, right? So not more than 850 hours, not more than 12 calendar months. Perform the capacity test. So after the initial, they have you doing it every like 6 months. It's like, oh my word. So what is the capacity test? Per STC, that would come with it. You gotta remove the battery from the aircraft. Rats, that's a lot of work. Connect the battery to the capacity tester, so they're not talking specific gravity, they're talking, we're gonna draw it down on amps, so it's gotta have an amp meter, your load, resistance, voltmeter, timer, and discharge it, and they're making sure that you get the 80%. So, pretty interesting. I'm teaching you this because I want you to know the right way, and you guys are gonna have to follow instructions when you get out in the field. I don't know if they changed this with Gill or what. I'm not sure this is common practice. It's correct practice, but I'm not sure it's common practice. So if you get into a situation where you're doing the annual, you're testing a battery, either do it correctly or check with the shop boss and be like, hey boss, this is what I have in writing. What are we doing here? To have that discussion with them. That came with my Gill battery. And what's supposed to be nice about lead acid batteries is they're low maintenance, they're easy to test. Oh, that just shot that one in the foot. So, wanted to show that to you, and just be aware of it when you get out into the field. Here was one spot, and I'll admit it's kind of buried, but in every service manual in between removing battery and I think testing reinstalling battery, it'll have cleaning the battery. So it's probably easy for you guys to get in there and read removing, read reinstalling, and skip over this pretty quick. But cleaning the battery is basically we're just cleaning it up with basically water. Let's see, I'll grab it just a sec to make sure. Clean cloth, bicarbonate soda. So back to baking soda and water. Rinse that off. We don't want the baking soda stuck on there. Allow it to dry. But brighten up the cable ends and battery terminals with emery cloth or wire brush. If we're installing our battery, we don't want to put a dirty terminal back on, dirty corroded terminal back on. Especially because coat battery terminals and cable ends with navel jelly. Not navel, that's a joke. That's somebody put in one of your labs. Petroleum jelly. So after you put it back on, that helps protect it from corrosion. Well, if that battery cable is installed correctly, when you took it off, it's a gooey mess, right? You got, yuck. So you take it off, you get that jelly basically all over the terminal, which means on the connection point as well, which we don't want it on there. So when you take it apart, you're gonna have to clean that off and basically remake that joint. Otherwise, you're gonna have petroleum jelly in between your connection, which we don't want. So when you're reconnecting those terminals, SMAT will skip the coat it because we don't want to mess. We could take a battery out, put it back in, take a battery out constantly, right? We don't want to mess for everybody. So we're not coating them with the petroleum jelly like the manual says because it's not going out to fly. We're not actually signing it out. But if it's not clean, and most of you guys weren't when you were doing them, make sure we're cleaning that with emery cloth, Scotch Guard, whatever, to get a really good connection on there. Make sense? All right, good. I think the next one was Leo. What documents are you working with? Just because the lab doesn't ask for that logbook entry, essentially do the work as you were. Now, as I was writing this slide, I was like, oh, what if they're like, I'm just doing a menial task, like welding two pieces of metal together. I'm like, okay. There's some of those that you probably don't have the manual for welding two pieces of metal together, or some of that silly stuff. But if it's take a battery out of an aircraft, put it back in, rig this, check that, put a tire on, do it in accordance with whatever manual, whatever aircraft. So this is what we love seeing right here. He's got his manual out and he actually had AC-43 to compare. It just made me smile when I saw those guys with that out. Now that said, this is not criticizing because it's an old junky aircraft. What might make me not smile if I was in an FBO with this picture?
Books on the, not a,
Say what?
not a workbench.
Yeah, it's not a workbench. So these have rivets on the back side of them. So between our tools, and that one's mine, our $100,000 paint job. You know, when I'm with Samaritan every once in a while when I'm flying the airplane, I just got to pinch myself and be like, I can't believe I can fly a $750,000 airplane. Like, who lets you drive a $750,000 car, right?
I don't know anybody that's got $700,000.
Right, exactly. Yeah, pretty cool. How many of you guys been in a ride in a $750,000 car? Not very many, but you know. So now given the paint job, it's not quite the same, but it's pretty close. So we want to treat the paint on these things, the finish, like it's now this one would only be a $150,000 airplane, right? But like it's a $150,000 airplane, and you wouldn't go set your stuff on the hood of a Bugatti. You'd put a cloth on it or you'd use a workbench. So just get yourself used to doing that, grab a workbench. Like I said, on the old aircraft, I'm not as worried about it. It's more we're just practicing for the future so we don't get in the habit of it. That we talked about in the other class. But that said, I don't want that little piece to overshadow it. The reason I put the picture in is that is what we want to see. Get the manuals out. That's what you want. I almost put in here the big reason, just to repeat again, ad nauseum. even so much if you have a problem and they come to you as the last mechanic to work on an aircraft, is when the airplane has a problem and the FAA comes to you as the last person to work on the aircraft, you wanna have documented what you followed and what you did. If you're gonna be a mechanic long enough, whether it's pilot error, and it's most likely gonna be pilot error, right, Brian? In the aircraft crashes. So most likely it'll be pilot error why the aircraft crashed. But they're gonna come looking through the logbooks, and even if it's pilot error and you got logbooks that, well, you didn't document, it's gonna be a problem, and you're not gonna wanna live with that. So pretty sure most aircraft, if somebody researched this for me, it'd be great. Pretty sure most aircraft don't become unairworthy because they got old and corroded. Most of them, it's some sort of an accident, a crash, and it might just be a ground loop, it might be they broke the engine, they broke the prop, yeah, it's typically a mechanical thing, so depending on how it gets logged or whatnot, the logbooks do get looked at towards the end of the life of most aircraft, if I can phrase it that way, to say, hey, who was on this last? All right, last one before our break. Lot of batteries, most batteries, Concord batteries, will all have it on a sticker. We might be missing some on, but so that one's real nice, right? Torque to 70 inch-pounds. The gills, I was looking, don't have it, so you gotta go back to that gill manual, like I showed you to get it. All right, questions on that before we switch over to fuel systems? Okay, let's take a 6-minute break. We'll start up at like 37 after. Well, it happens. So
It looks a little old.
Yup.
I will.
So I'm like, what in the world? And I'm trying to do a better job of no grade until we have the correct checkbox. So if you are Steven, Yoder, Isaac, or Abed, either see me or Dean and have us recheck off the checklist. Because I don't have record that you showed us after it was painted, but you turned in your lab. So if,
I'm gonna show you my phone.
okay, all right. That was what I was wondering, is if you did the battery part and then just submitted the lab, and I don't have the other. So if you're those guys, show me, show Dean, and I'll be grading more stuff today. So fun stuff. All right, I'm gonna get rid of this page. I can take notes. And we will launch into capacitors. If you were overhearing, we still don't have a good answer for that stud number 10. We think it's buried in a document that cost $110.
Yeah, it was like 151 bucks.
So we're probably not going there. We found clues that you might be able to do smaller ones. That kind of breaks the question, but written question, they like number 10, and we'll just leave it at that for now. Now you know how to answer the written. All right. Whoa. Do I have anything to talk about on that one? How do we know how much fuel is in our tanks? Now, what's interesting is you guys have not had fuel systems yet, right? Coming up, that's why your aircraft got moved in, actually, because you're going to deal with the fuel systems on the Apache, and nice, that's not very nice out there. So we're going to launch a little bit into fuel systems, not so much trying to actually teach you everything about the fuel system, but normally we monitor the level of our fuel in our fuel system with electrical equipment, and that one is this class. So how do we know? Common way, the old version, is with this guy here. I think this is actually a class display model. It's got a nice clear plastic piece on the edge, so you can actually look in there and see the resistor moving around. Variable resistor, so I'll pass that around. I'll admit I have not changed any of those personally. I had some mechanics change a couple for me. But I wasn't, I was a pilot at the time. So I haven't personally had to deal with them. They're pretty easy. It's just a couple screws on the top of the tank and they come out. Basically, you've got a float on the end of an arm. When the tank's empty, the arm's down. When the tank's full, the arm's up. When you follow the maintenance manual, which you'll do in the next class, for is this thing functioning? Cessna typically actually says it's got to be accurate when it's empty, and generally in the neighborhood when it moves around. It's not so much accurate on the way it goes up. That's pretty wild, but that's kind of how it is. The other interesting part is basically what we do is we send that thing a positive voltage coming out of a meter. The voltage goes through that resistor and typically right into ground in the shell of that thing. So it's actually providing a path to ground. This thing's got fuel splashing around on it. And for me, I'm just like, really? We're gonna put something that could potentially cause a spark inside our tank, splashing around with fuel in it, but I don't know if they're figuring no oxygen. They just, yeah,
So this is about a year ago, on our snowmobiles.
Yeah.
A giant recall, like 250,000 snowmobiles. And we had to take out the fuel sending, or the fuel level resistor and change out like all of them. On like over, at our shop, we had like 500 selected.
so they had a similar situation.
An issue is spark and blown up.
They should have just left it with the old float with the finger, huh? But that's how it works. I don't believe that they're really crazy sealed in there. What you're gonna find in fuel systems class is we actually have motors that are submerged, that we're running electric motors in the fuel. And the fuel is what cools the motors, just this wild, well, no oxygen mixture, so I guess we can't start a fire down there kind of situation. But I don't wanna get too far off in there, it's just crazy to me. But so that's the old common version of what we're doing. And I asked my myself to draw a wiring diagram for what this would look like, and part of it is, I just wanna kinda show that really it's kinda so simple that, you should be able to memorize the wiring diagram essentially for these. Oh, negative is sideways, so, simplified obviously, I'm not gonna draw my master and bus bar and all that stuff. So, basically off positive, we're gonna go through what's essentially an amp meter. Now we're gonna convert the needle on our amp meter over to empty or full, right? But essentially we're going through an amp meter, yeah, we'll leave it at that. Out of that amp meter, we're going into our float, that's a variable resistor. And out of there it comes to ground. So the less resistance we have, the more amp draw we have, and the needle moves, right? I don't have memorized which way is which on new ones or in the manual for these things. You can often check, and they'll say put it at the empty position and check resistance, put it at the full position and check resistance, so it'll tell you what side there are. And I haven't done it enough to know which way is which. But that's the system for, hey, how much fuel's in my tank? Pretty simple, right? Making sense to everybody? Cool. Next slide, I pulled off Cessna's drawing, one of their actual drawings for it. So, might be a little hard to read where you're at, but we got our instrument bus is basically what they're saying with a 10 amp circuit breaker. And following the wires, I'll highlight them. This one comes to here. This says fuel left-hand tank. So here's our gauge, which is, it's essentially that amp meter. But, so we're going through the gauge, over to number 3, if you follow the notes, is our fuel level. So basically that's a variable resistor in there, and right to ground. So, oh, that's kinda cool. So that's our left-hand tank. Our right-hand tank, they go jump over to the cylinder head tap just because they landed it on a terminal. We gotta power this guy somehow too, right? But then they go over to the fuel right-hand tank, basically amp meter, and then up to my variable resistor again, down to that one. So, pretty simple system for how we check the level of fuel in our tanks. And if you have to troubleshoot those, the manual will give you the step-by-step of checking power up to the point, possibly pulling it out, checking the resistance. And if you have to make an adjustment on where it reads when it's empty, it'll tell you how to make that adjustment. And basically it will be an adjustment on when it's empty, and they won't give you much else help anywhere else. So, pretty simple. You can have more than one in a tank. You won't often see the float style with more than one in a tank. Yeah, I'll just leave it at that. But you could theoretically have more than one in a tank, and then the engineers just have to decide, do I put them in series or do I put them in parallel? And it'll be the same principle as what I'm going to show you for the capacitive style in just a second. Let's say Brian's got a student in the plane. I like using you for an example just for the fun of it. And his student is terrible at flying coordinated, as we say, which is having the ball in the center, or he's skidding. He's got the back end of the plane out and all the fuel's whipping out to the outside of our fuel tank. If my fuel tank is shaped like that in my wing, there's the aircraft tail, well, I'll give you half of it. If all my fuel has sloshed out to this side and my fuel, what do they call it? Pickup. Yeah. Fuel level indicator, depends on the brand probably, is over here. This is going to show, hey, I don't have any fuel in that tank. So it is pretty common as you're flying around for that fuel gauge to be moving around, because if I'm not coordinated, my fuel might move around. The other one is if I'm taking off or landing, I might might slosh the fuel towards the front of the tank, or I might slosh the fuel mostly towards the back, which would typically be the case on like a takeoff. The Cessna 206 that we fly for Samaritan seems to be exceptionally sensitive to this. I don't know if it's my long-range tanks or what, but when I take off, I'll go from saying 10 gallons in my tank to 2 gallons. And all of a sudden I go, where did all my fuel go? And basically, my fuel went to the back of the tank as I took off, and my sensor's like, oh, there's not much in here. So why I bring that up and spend a little time is when you're checking these things or servicing them, it's gonna be pretty important, and the manual will say, make sure the aircraft is parked level or leveled even in some cases, to make sure that you don't have a little bit of fuel sloshed one way or the other when you're setting this up or checking it. Cause, yeah, not the most sensitive things in the world. Alright, so those are pretty straightforward. You look through the manual, there's not a lot of complication there. The fun ones, which is what larger aircraft are going to, and I think even smaller, higher tech aircraft, are using these capacitors. So I introduced these the other day when we were checking capacitance. But basically, we've got these fuel level sensors, and it's fun to play show and tell, so we'll pass a couple. Oh, that's a big dog right there. We'll pass a couple around the room. I don't think that's a Cessna, just because, well, you know, too big. That'd be a really thick wing. And it is a capacitor. I did double check this morning and tried to read the capacitance with my meter, and it just says there's no capacitor there, because it's in picofarads, which, if you remember, picofarads is millifarads. So we're talking tiny capacitance, but basically these are one aluminum, I'll stick with aluminum, one metal shell, one plate on the outside with another plate on the inside. And remember, with our capacitors, what gives them area to store is, or ability to store, is the area of the plates. So if I change my plate size, my capacitance can change, but when it's installed in my aircraft, that'll be fixed. The distance between the plates can change the capacitance, but installed in the aircraft, that's not gonna change, so that's fixed. And dielectric value of the dielectric. Well, in between these plates right now we have air, right? So air has a dielectric value of pretty much 1. I think they go 1 point something. But air has a dielectric value of pretty much 1. If we fill our tank up and put fuel in it, our fuel typically is going to have a dielectric value of between 1.7, 2.8. I kind of scoured the internet. It was kind of like looking for the number 10 stud thing. Going, what's the dielectric value of avgas? And it just wasn't coming up. I could find it in these really obscure places that didn't prove anything. So this was the closest I could get for giving you a rough number of what the dielectric value is of avgas, but it's more than 1. So basically, if I raise my dielectric value, I will raise the amount of electricity I can store on my plates, or I'll raise the microfarad rating of my capacitor. So with a full tank, I'm going to have a better capacitor than I'll have with an empty tank. What was interesting on here is water had a really high dielectric value. Hopefully we never fill our tanks with water, because that would be a problem, right? And there's not enough water in our fuel to make a difference. But it was pretty interesting that water was crazy high. I almost want to do our next test we're going to do in the lab to see. I might do one in the water just to see what happens. We're going to do it in mineral spirits, which is pretty close to avgas for dielectric value. Yeah, we might do a water. Here's another one that's showing dry air is basically 1, just a little bit over 1. And it gives some other dielectrics, paper, glass, depending on what kind of glass, but water, 80. Woo. ones come out of, they use these for actually checking salinity in water, so the temperature and salinity will change the dielectric value of water, which is kind of wild too. Alright, so actually I want to be in this screen to start. This one is showing all the different locations that we might have capacitors for checking our fuel quantity in wings. So you can see they spread them all out. I did not pull up a exactly specific aircraft to make this point. I'm going to give you guys a hand-drawn idea because I couldn't find a good picture. So let's say we've got an aircraft wing. Let's see how I do. Yeah, that's not bad. That guy is climbing. That's woo. It's like an F-16 climb, isn't he? All right. There's my fuel tank in there. And we'll draw the same. Oh, that was descending. I want you descending. We'll draw the same wing in a basically level flight configuration. So let's fill our tank half full. So we're half full of fuel, and yeah, does that look about right? All right, I'm in the neighborhood. So we'll draw our sensor. If all we did was put one in and we don't know where we're going to put it, let's say we put it up here. A lot of times Cessna will do that, or maybe they put it towards the back. If all we did was put one in, we're going to put it in and we're going to get all the stuff calculated so that when the fuel level's halfway on the thing, the gauge will show I got half a tank. Well, the problem is when I go to take off, just like the old Cessna ones, well, now I'm going to show basically an empty tank, right? So what they did is they said, hey, these things don't weigh hardly anything. And we don't like the gauges bouncing all over the place and confusing our pilots when they're climbing or descending. So if we put, oh, I didn't draw the tank in this one. Maybe it's an integral tank. You'll learn about those. If we put a second guy in here, and basically all we have to do, if we have capacitors, and they can, depending on the manufacturer, but if I wire my capacitors in parallel, and hook them up to my gauge, however it decides to read, I'm going to have twice the capacitance available, right? So they'll just go in the little adjustment for it, and they adjust to say, hey, whatever was going to be half, we're going to make it half of that microfarad rating because I'm stacking them up together. So in this case, we'd still read half a tank because we're going to mathematically, or using resistors, however you want to phrase that, they're going to have an adjustment to say, where is half a tank? Well, when I'm climbing and I have two probes in, the microfarad of this guy is going to say, you're empty. The microfarad of this guy is going to say, you're totally full. But it's basically going to average those out because they're going to be wired and usually in parallel. Well, it'd have to be in parallel because in series, there's always going to be less than the smallest. So we know it's always parallel. There we go. A little logic. So it'll average that out. One saying empty, one saying full. Averages it out and says, oh, you got half a tank, even when you're climbing, and it's like that. So there are times, like possibly this picture, now this one might be exaggerated, but depending on how connected those tanks are, they might only give you a right wing fuel level. And even though I've got multiple sectioned off tanks and whatnot, we can still, I'm going to use the word mathematically, put our capacitors in parallel and average them to say, oh, I'm averaging this area. So kind of cool how that lets you really get away with some fun engineering stuff to know your fuel level averaged out. Almost all capacitor type sensors are going to have some sort of way to adjust them. I'm not going to go in detail on any specifics, but basically there's an adjustment for when the tank's full, okay, and that'll adjust the gauge to full, and adjustment for empty, and you get empty. So this one's controlling 2 tanks. It's hard to read here. I think it's this guy. Yeah, one's right and one's left. We'll pass it around. Hard to read for you, but basically one of them is empty. So here's my empty adjustment. Here's my full adjustment. And I think that was the right tank. Empty adjustment, full adjustment on the left tank. This one's got it a little bit different, full adjustment. It's interesting they do empty on both the auxiliary and the main. I don't know if they don't care where full is on the auxiliary. So I'm pointing that out that they're there. Once the aircraft leaves the factory, there's really no reason you should ever have to change these. So if you got to a point where you're like, oh, I think it's reading wrong, double check, second guess yourself and say, am I sure? And absolutely follow the manual if you ever had to do that. That's not something you just walk up to on a 100-hour and you're like, let me tweak it a little bit. Because they absolutely want you to follow the manual on those. All right. The last couple slides in this one are not stuff the FAA is going to test you on, but stuff you want to know. So far, these ones are more stuff that the FAA is going to want you to know, capacitance and how it works, and if it's empty or full, the dielectric changes. So questions on these guys for now? Cool. We're going to take a break / go to lab in a couple slides here, and we're going to fill up a can with our mineral spirits and hopefully watch it change. And then just for the fun of it, we'll do it with water and see what happens. That'll be fun. All right. There are other ways to check your fuel level. They haven't made their way into your textbooks yet. They haven't made your way into your writtens. So this is kind of for your info. They've got ultrasonic transducers, which basically they're bouncing a beam back down, and the noise, if you will, is going to hit it, come back and say, oh, I got about half a tank. When you guys went through materials and processes, you kind of went through how sound waves bounce around. So that's a signal that's getting a little bit more popular. Laser pulses are basically they're measuring the reflection off the fuel, right? And lasers or light takes a certain amount of time to travel. This one blows my mind. So they'll measure how much time it takes for the laser to hit the fuel and get back, and they can tell the difference between 6 inches and 10 inches. Wow, that's crazy. But that's one way you can do it. And another one is radar, pretty similar to ultrasonic, right? But this one's using essentially noise. That one's using electronic waves, and doing a very similar thing where they're just going to bounce a signal off, and wherever level we're at, bounces back. So I wanted to show you those because you get out into newer airplanes, airlines, it might be one of these, not one of these. So just be aware that there are more options out there, and they're going to start showing up. But these are the main two. And I talked about it once, but if you are checking the capacitance of one of these things, if you use the boxes that we have, 950, yeah, I think it's a 950 something or other. If you use those wires that are connected to each other, we briefly talked about the capacitance of those wires, just because they're so close, is pretty close to what the capacitance of this is already, because of the proximity to each other. So if you're measuring one of these, don't use wires that are connected to each other. Use jumper wires that are split apart, so that you're not reading the capacitance of your wires, but you're actually reading the capacitance of your fuel sensor. There is a lab that I think probably opened up while I was lecturing. Now, there's 5 small capacitors here, and they want you to use the 950 box and check the capacitance of these things. So I only have one set of these. I was looking around to see if I have more. So I'm gonna say, and I'll probably even do it, we'll put a chart, maybe we'll zip tie it to the little bag or something to say, hey, who wants to be next? So that you guys can roll through this and all get through checking your capacitors. If you need my help, Dean's help, let us know. You could go back to the lecture I did on capacitors, but I held that lab back because a lot of the questions they asked, we answered in this lecture. It'll be easier to answer the questions now versus hunting through books and trying to figure out what the answer was. All right, make sense? Good. Let's give ourselves 10 minutes, because I gotta go get it set up. But at quarter after, we'll meet in the lab and we'll check this guy and we'll see how the capacitance changes. After that, we're gonna bump back in here for a couple slides to warm you up for tomorrow's lecture. So, quarter after, we'll meet in the lab. comments about electric being hard. No, I'm just kidding. It is hard.
Theoretical. I mean, it's not theoretical.
All right. What I wanted to do was just kind of run through, just to warm you up on our voltage generators again. We're going to go really deep tomorrow, but a lot of times this is where we start to lose people. I'll grab that one. This is where we start to lose people with electricity, and they're not that complicated, so I'm hoping we don't lose you. So, if we take a wire and spin it through a magnetic field, we're going to induce a voltage, and voltage equals amperage as long as there's a circuit connected to it, right? So that's what we have in a typical generator. When we're using an alternator, we switch and we put the field on the inside and the wires on the outside, and because we don't have brushes, it's an AC voltage that we produce, but then we send it through diode bridges to make it DC. So we're going to stick with, at the moment, a DC generator, assuming the rotor, the inside part, is our armature, which is where we're harvesting our power. So if I have a generator running, if I spin it faster, the faster I spin it, the more voltage I induce, more voltage or amperage. So that's one way to do it. But at a certain RPM, say I'm running my aircraft at 1500 RPM, that's going to give me a certain RPM once I go through all my pulleys. So at that certain RPM, the other way to change the voltage output is to change the strength of these magnets, right? If I make these magnets as strong as I possibly can, I'm going to have the highest voltage I can possibly make. And the strongest I can possibly make them would be going full field. It would be saying I want my full voltage that's available in my system through these. So on a 12-volt system, when this is running, usually what we do is we say we'll allow this to put out 14 volts, but at 14 we say no, we don't want to go above that because we're going to start cooking our battery, cooking our components. So we start limiting how strong these magnets are. So that's what we're going to talk about tomorrow with our voltage regulators. I'll cover this one up. You don't need to know what that last terminal is for yet. That's later on. But today, I just want to briefly go through, because we talked about it. I threw up a picture of the one that's on the troubleshooting board, just to remind you that some of them, the right coil is the left coil, and the left coil is the right coil, depending on how they make it. The giveaway is the two sets of contacts that are connected with a bar. Those are going to be the ones that are controlling our field coil, our field voltage. So on this guy, I've got two coils connected with my contacts. They're going to be controlling my field voltage. That's, I think, the same one with just a different picture. So two that are essentially connected, that's controlling my field voltage. When the contacts are made, when they're connected, I'm giving it full field. I'm saying I want as much power as I can possibly get. So there's two reasons I might open those contacts, the two coils. One reason, with the tiny wound one, is if my voltage gets too high. So on a 12-volt system that I'm putting out 14 volts, I'm going to adjust so that contact starts to open at 14 volts. So if it goes above 14, the contact opens. And the voltage drops because we just said, hey, don't make any more voltage. So then it closes again. And then it's like, oh, you're too high again. And then open. So we call them vibrating point contactors. So it's just going to sit there and buzz, but it'll hold our voltage output at 14 volts. So that's what the one guy on the end is doing, and we'll deal with the wiring diagrams tomorrow. I don't think we do them today. The really heavy wound one is our full output from our generator, from the armature, is running through this wire. And it runs through that wire, and if the amperage in there gets above what our generator is rated to be able to handle, so if it's a 50 amp generator, I'm going to set the spring on that guy, because I can adjust them. I'm going to set the spring to say, hey, if I get more than 50 amps coming through here, that's too much. We're going to open that little contact for me. So whether it's the voltage gets too high or the amperage gets too high, we're going to open those contacts. That's why those are connected together. On all of them, it'll cut the power to the field, which is reducing our output. Well, once it's reduced, then they close again. So both of those are gonna be a vibrating point. This one doesn't open until the amperage through that big heavy wire, because my full output from my generator is going through there. The amperage is too high, he opens. If the voltage is too high, he opens. The last one on a 3-point is our reverse current cutout. And basically my power goes through this one and then goes through that one. And if the power is going the correct direction, this guy will end up getting closed. If the power starts going backwards, you notice when we were testing our generators, if we held him closed or when we flashed the field, we motorize our generator so the current is going backwards through the generator. If the current's going backwards, the magnetic field of this big heavy guy is basically going to open that contact back up. And the reason it opens it back up is it's spring open to begin with. So if you look at these just sitting here, before I put any power to them, it's spring open. So I'm not going to be able to make power and actually send my power through here. But what happens is, as the generator is starting to spin up and we start to produce a voltage, there's a tiny little coil underneath the big heavy guy. When I say tiny coil, it's a thin wire. And if you look at these, a lot of times you can find where the thin guy pops out underneath the big one. Dean likes to call him the wimpy man. So the wimpy man, when our voltage gets up above, and usually it's 12 volts or wherever we're set, to say, well, it looks like our generator's running and it's higher than our battery, so I won't have the back current. Because if my generator's running but I'm not getting enough voltage, and I close that switch, the current's going to come backwards, right? So once the generator's running, I got enough voltage that I'm going to push it into the battery instead of the battery pushing it back through me. When the voltage is high enough, the wimpy guy will say, yep, okay, we're ready to start working. And he wimpily closes those. Once they're closed, because the voltage is high enough for our generator to be pushing into the battery, then our amperage that we're generating, the heavy-duty dude comes along and he says, I'll help you, wimpy man. And he helps close it shut. So it's a wimpy guy to say, let's start making power. And then once you start making power, and the power's going the correct direction, the big strong guy says, I'll help you, wimpy man. And he holds it closed. Now if we get into a situation where our generator stops making voltage, so typically it's not going to be these guys are opening because they're just opening when you max out our voltage, right? But if we get into a situation where it's trying to motorize this again, when the power, if it can come backwards through there, and it actually has to come backwards for a slight amount of time, once the power is going backwards through that coil again, this guy's going to go, the big heavy guy is going to go, oh, Wimpy, I'm not on your team anymore. And he's a lot stronger, and he'll overpower Wimpy Man. And he'll open the contacts basically back up. As he goes, I'm going the other way. Now, the tricky part with that one is all it is a magnet, right? So a magnet to what he is drawing himself to. The other side of his magnet is not a north-south, where the big strong guy actually says, I'm fighting you, I'm working with you, blah, blah, blah. But what we have going on is we've got a spring that's, I'm going to say, giving us positive pressure to hold it open. We've got a wimpy, we've got a wimpy coil, and he's going to say, no, I'm going to say negative to close you. If we don't have anything going on, it's open because our spring's the strongest. Once wimpy gets strong enough, he'll close those contacts, and if the voltage, the amperage, excuse me, is going the right way, our strong guy, in the correct direction, he's negative. But if we start putting power the other direction, he'll switch to positive, and this positive plus this positive will be enough to open it back up. Now, if you really overamp the guy negative and go really far positive, what happens is it turns it into a strong enough magnet that This guy will not only overpower Wimpy, but he'll overpower the spring as well. And so he'll go from saying, we're gonna make it open back up to, whoa, I'm really strong. And he'll suck it back down. And that's how on the test bench, if you're messing around, which you might not want to, if you just bypass that guy for too long, you'll establish amperage going the wrong way. It's a reverse flow, but it's so much amperage going the wrong way that he turns back into a super strong magnet, overpowered Wimpy, and he goes, ugh, and he'll close it down. About the only way you can get it to do that is by physically holding it to get the amperage high enough to do that. Usually you can't do that in an aircraft. What'll happen is it'll open it back up, we stop making it, now we don't have flow. So, all that to say, intro to those three guys are, we've got, these two are connected, so voltage gets too high, opens the contacts. Amperage gets too high, opens the contacts, and those are the field ones. We're just sending our field through the contacts to ground. And reverse current is Wimpy closes first, then the big guy helps him, unless the current's backwards, then the big guy starts fighting. So, we're gonna go over that in detail tomorrow, but I'm hoping that if we kind of talk about it a couple times, you go, oh yeah, that's not that complicated, and it makes sense. All right. Cool. Questions, comments? To lab we go. I'm gonna dip that capacitor into distilled water. We got this little steam. We're gonna see if it makes a difference.
I wanna watch that.
In case, for those fuel sensors, capacitors,
Yeah.
where do I find that in the textbook, or would I find it in the AC-43?
Textbook's gonna be an airframe. Is there a specific question you're looking for?
Yeah, it's like, which of these types are, which of the following components are
Not a lot of
capacitance?
It's not that long, actually.
All right, so the reference capacitor would be, because that's what I'm saying. Do we have a heat exchanger anywhere? Attitude gyro. Variable capacitance transmitters.
That's the one.
Well, so that's, it's varying because of the fuel level.
Yeah.
So, you know what, I probably should spend more time. Some systems will have a capacitor in there to give you, they call it reference, to give you, hey, this is like empty. So, you're gonna want to put reference. And then the microgrid circuit, basically that's just the circuitry of some stuff.
Is that,
That's those adjustment boxes.
would that be a capacitance type fuel?
So that's this guy.
Yeah,
So
that-
this circuit
But
is
don't you have to
microgrid.
have like a quantity indicating system to tell, would that be the indicator system?
Well, this doesn't indicate, it's gonna get plugged into an indicator, which they don't give us as an option.
But is that something on one of the lab?
Yeah, you're going.
If I added it, yeah.
No, I can
It
only,
doesn't
I
say
only,
on all of the components, because we have to add wires.
So basically it's asking for different types of components in a fuel
My,
indicator system.
yeah, my guess is he was looking for some ball sensors,
Okay.
so threw in their attitude gyro.
What about an inductor? Actually, inductor is parallel.
Threw in heat exchangers.
But the very variable capacitor transmitters,
That's these.
that's the one with the,
That's this.
that's that. Okay.
Yeah, because it's gonna vary in capacitance, whether it has fuel on it or not. The reference capacitor, I'm gonna go double check in my office. Inside these or inside the gauge, they might have a kind of standard like this.
no.
That gets messed with those as you're adjusting. So I'll double check that answer real quick. Cleaned up? Yep. I'm gonna go with no. We still have corrosion. check that in.
Yeah, they do.
Reference capacity, variable capacity. I don't know if
there's one question that asks, what are components of a fuel level capacitance sensing system?